So on this problem, we're still burning octane, but we have more air than we need. So we are required to find the dew point of the product if the pressure is this. Okay, so I think these problems you should know by now. They always start with us balancing the equation. Presence of oxygen and giving out carbon dioxide plus 9 waters. I'm just putting this because on the previous problem I think we did balance this equation, and this is what we ended up with, 25/2 here. So this is our balanced equation for what we call octane, but we have to take in those nitrogen. I think it was 47 nitrogen. I have to edit both sides. 47. So, but most likely if you're doing combustion, maybe inorganic chemistry, they focus in this part. But if you're doing air fuel ratio, I think this part is important because air doesn't come with oxygen alone, unless if you're just purely feeding your engine with oxygen, of which in this case that's not the case. We are feeding our reaction with air, of which has a lot of impurities, and all the impurities is nitrogen that you're focused on in this case. So we know that it's given that we have this much of air. So the reaction to be like fully combustion is need 12.5 moles of oxygen. So if we're giving this thing 200, we're giving it like 2 times than it need. So it's getting 12.5 to handle the reaction fully, and some extra 12.5. So that 12.5 will literally come out as extra 12.5 oxygen, right? Considering here we're not giving now 12 divided by 2, we're giving exactly 25. This 25 oxygen, the first part will just handle the reaction. That is enough. That is enough oxygen. And then this one is extra, or in the most chemical term we would have said excess. So I think everything is balanced out. But the problem that for us to get that more that times 2 oxygen, that means we also, if we're getting this thing from air, we also have to unfortunately time by 2 nitrogen. So if that nitrogen was 47, but now it will be 2 times that 47, so we end up having 94 here. 94, right? And then on the side we'll end up having 94. So this thing is now, I'm happy with it. So let's try to find the total number of moles in the product, right? We're going to have carbon dioxide in a product that will give us like 8 moles. We're going to have water, it's going to give us like 9 moles, and we're going to have like oxygen, the leftover oxygen, let me call it oxygen, and like it's the leftover or excess, then it will be 12.8. What did I take account to? And then we're going to have nitrogen, of which we said 94 moles. All these things have moles, right? So if we have to find like the total number of mole, sum all these things, I think we're going to get, you add the first one, the second one, third one, then the last one, then you're supposed to get you get that 123.5 moles. That's a number of moles that are in the product, right? So when we know that, we can now move forward. We can now find the mole percentage of carbon dioxide. Will be how much moles carbon dioxide is giving us, 8 all over 123. We're going to get something. We do that thing again for maybe H2O will be the same thing, getting 9 all over 123.5, remember, and then oxygen going to get that what oxygen is giving us, excess 112.5 all over that 123.5, remember. Then that nitrogen is going to give us, should be the biggest, 994 all over that 1.235, right? And then if I compute this, I get that 6.447%, I get 7.2%, I get 10.12% for this one, obviously big, 76%. So this is our mole proportion for each element, right? But they did give us some pressure. They gave us the pressure of let me say pressure total was given to be 0.1 MPa, of which, what happened here, MPa of which is somewhere around 1000 kPa. Okay, cool. But now we're trying to find the pressure on the water part. Find the pressure on the water part, it will be pressure partial of which is partial of water should equals to pressure total multiplied by its contribution here. It's contributed around where is water? 7.2%. so if this is 100, that's a percent, so we're likely going to get 7.2, exactly 8 as 8 years, but kPa. And then we're going to call this P₈, and then go to our steam table. And then I think let me go find it first. And then on my book, this number is between 5 and 7.5, and here it did it 2.87, and here it's 40.29. And remember, these are temperatures, these are pressures. So we have the pressure we're trying to interpolate here, and if I do the interpolation, I'm going to get T₈. I'm getting 39.667 degrees Celsius. And remember, if you can interpolate here, I have a very good video showing you how to interpolate using a calculator quickly. So otherwise, thank you for watching. That was second example. We're looking for some dew point of temperature given that pressure. If we have excess oxygen, we're burning octane using mole analysis. That's what we did. Thank you for watching.